The name of the talk on the schedule is Go Anti-Patterns. But while writing this talk, I realized that what I was after is a way to explore what idiomatic Go is. So I'll cover a few of the anti-patterns I've come across as a way to do that. But first, I'm going to introduce myself. My name is Edward Muller. I'm known online as Freeforms. I've been an engineer at Heroku for the last 6 years, but I've been writing software since it was distributed on 5¼ inch floppies. In 2012, I wrote my first line of Go and pretty much fell in love. If you Google these words, why I like Go, a GitHub gist I wrote a few years back is the top result. I wrote that gist because at the time I was being asked this question a lot and decided to summarize my thoughts in a post I could share. The gist lists some language features, but overall, runtime, tooling, standard library features are more prominent. Things like concurrency with Go routines, garbage collection, memory safety, lack of a package system, built-in profiling, and others are called out. These features drew me to Go and are often cited as why someone likes or should use Go for a project. My advocacy for Go and the rise of Go internally eventually led me to the role of Go language owner at Heroku. So what does a language owner do? We're the engineers responsible for supporting customers using a given language. To the best of our abilities, we internally represent the community behind the language we support. If you've deployed a Go application to Heroku, had a support ticket escalated to the Go team, read a Heroku Dev Center article on some aspect of Go, or started with one of our Go sample programs, then you've interacted with some of my work. And I hope you've had a good experience. If you didn't, please let me know after the talk. So why do I care about idiomatic Go, though? Language owners provide end-user support. As a result, I've had the opportunity to read, comment on, and help organize a lot of Go code, both internal and external. When a customer has an issue, opens a ticket, I'm usually the one reading their code to try to figure out what's going on, what are they trying to do, and why is it broken. Go is also a primary language inside of Heroku. I'm often asked to provide guidance and/or review code when a team adopts Go. This process is always easier, faster, and less painful when for both parties, when that code is idiomatic. But a lot of that Go, just like the Go I started writing 5 years ago, and frankly, sometimes still write today, isn't all that idiomatic. I don't say this to chide anyone. I mean, it's natural to bring idioms you've learned in other language to your new language. And Go is a newer language. There are fewer native Go speakers than there are for many older languages. A lot of my initial Go code looked more like Ruby, got drunk, picked a fight with some Go routines and channels, only to be locked in jail for the night. So reading Go code from this diverse group of software developers has helped me appreciate some of the more subtle aspects of Go. Those aspects weren't listed in that gist. These aspects are reflected in what I'm calling idiomatic Go. But again, what is idiomatic Go? As best as I can tell, Go code that is idiomatic adheres to the design principles of the Go language. Those are orthogonality, simplicity, and readability. The Google Tech Talk introducing Go in 2009, Rob's blog post, "Less is exponentially more," and the Go proverbs all either directly talk about these design principles or reinforce them. Let's cover those traits quickly. Number one, orthogonality. In programming terms, Orthogonality means the pieces are independent from each other. Changes to one part, a type, a package, the program, has minimal effect to no other parts on the others. The Go standard library contains many orthogonal pieces. My favorite examples are the interfaces in the I/O package, I/O reader and I/O writer especially. Each of these interfaces are implemented over 700 times on my system. These implementations vary greatly from reading or writing local files to network connections, images, streaming logs, and others. A change to one has no effect on the others or the interface. Said another way, the interfaces and their implementations are orthogonal. Number 2, simplicity. This is often talked about as reduced complexity. Go does this by removing features found in other programming languages. The Go language has a regular syntax. It doesn't need a symbol table to parse it, and there's no classes. Methods can be added to any type. It has no inheritance, and so on. You know what? Go doesn't have generics. In essence, Go embraces less is more and promotes simplicity. Number 3, readability. This is usually referred to as reduced clutter and noise. Go does several things to promote readability. There are no header files or forward declarations. Everything is declared exactly once. It's an error to redeclare a variable in the same block. There's few keywords, leading to a simple, unsurprising syntax. Type derivation and the declare and initialize construct reduce typing and help avoid stutter. So, given those traits, how do we know idiomatic Go when we see it? For me, at least, it's always been easier to identify code smells, things that somehow aren't quite right. So, I've identified a set of Go anti-patterns from smelling a lot of code. As a way to spot design issues and help guide you to more idiomatic Go, let's cover those. First one, tiny package syndrome. This usually appears with a directory structure that looks similar to this. Lots of packages, each usually containing a single file, especially if they're missing tests. In this particular example, all of these files store and retrieve things from context. They're all grouped by kind under the notion of being related to context and are therefore located in a context directory. This is an archetype, though, so while I show context here, this isn't context-specific, but we will cover context later. The content of most of these files look like what is on this slide. Key type and constants are defined along with one or more with some type and from context functions. This context-related package and the original package often have the same name. If not, CTX or context are appended to the package name in order to avoid import conflicts. A better way to do this, though, would be to collapse the directory structure like this, making this a larger package named context, containing a bunch of with some type and some type from functions. But an even better way, and what I would generally recommend, is to make those functions part of the original package as seen here. This keeps the complete API of bar located in a single package. It's not spread out across multiples. This isn't the only way tiny package syndrome shows up, but as a general rule, look for lots of small packages grouped by kind or otherwise organized in some hierarchy with a small number of files per package, especially if they don't have tests. Number 2. I don't actually have numbers in these slides, so I will eventually forget. Premature exportation is closely related to the last anti-pattern. Developers have a drive to taxonomize things, splitting them into the smallest pieces. This segregation, this excessive over-taxonification, in order to derive the smallest, driest piece of code, can result in many small packages. This has a follow-on effect, though. In order to make the packages usable, most or all the package contents need to be exported. This ends up becoming a pattern, and suddenly every type, function, variable, and constant in every package is being exported. For instance, in this code, why is bit exported if it's just used internally? When I see this, I often have to remind others that Go has no type or object hierarchy. Another way this anti-pattern emerges is when packages that are internal to a project are exported wholesale. In the project presented in this slide, anyone who can access the project's source code can use package foo and package bar. But the developers of project only intend for those packages to be used internally. They aren't expecting feature requests from the outside. They don't discuss changes with others, etc. But along comes other project, written by another team, and they see something in project's code and they think may be useful, so they start using it because they can import it. The developers of project can instead signal their intent that foo and bar are not for external consumption and place the foo and bar package in an internal directory. Packages located in an internal directory can only be imported by internal's direct neighbors and their descendants. Here the developers of outside project can't import foo or bar. They can either copy the code into other project or start a dialogue with the maintainers of project about their needs with the intent of making some or all of those features publicly available. In summary, don't export types, variables, functions, and constants until there is need to do so. The driest, smallest, most segmented packages lead to the need to export everything. Keep packages that are not meant for external consumption in an internal folder. This relays the expectations the authors of those packages have around who they expect to use the package. Speaking of packages, package util. Here's an extraction from a util package I've recently run across. The name util says nothing about the purpose of this package. In Go, package names have semantic meaning. The name provides the context the users of the package need to understand what the package provides. The name of a package should describe its purpose, not its contents. The only part of the package import path that matters is the rightmost name. That name is what is used when referencing the package's contents in your code. ICUtil packages often form when a project is doing a lot of group by kind and has some pieces left over. Where do they end up going? Let's just stick them into util. Do you notice anything particular about these functions, though? Well, they all generate things. So why not make a generate package instead? Now there's generate.randomBytes, generate.randomString, generate.cert. The name generate conveys the purpose of the package. The function names specify the what. So to summarize, package names have semantic meaning. Those names should describe the purpose of the package, not its contents. The only part of the package import path that matters is the rightmost name. And util says nothing about the purpose of a package beyond some grouping of bits. The config structs anti-pattern. Maybe config structs, maybe option structs, really the same pattern. I've seen even written code that essentially looks like this. There's a command package, or CMD, that contains one or more configuration types and functions dedicated to parsing the environment and configuration into variables, values of those types. If we look at the value that the cmd.newConfig functions returns, we'll see that it has a total of 28 members. Back in our program, we see that the config struct value is blindly passed through to other functions. Does db.newConnection have any need for the input format member of this config struct? Does doer.newFoo have any need for the batch size member of this config struct? Can we even determine from the function signatures what members of the config structs are used by these two functions? Nope. One way this anti-pattern develops is when a developer cargo cults the mantra that package globals are bad. They decide to stick those globals into a config struct and then pass values of that struct along in their entirety everywhere those globals were used before. Similarly, this example shows an options struct. The code base this was extracted from contains several methods like doThing, some simpler, but some way more complex. All use a subset of the members of the options struct. Additionally, there are multiple option structs in this code base, each different, just in different packages. Just like the config example, it's hard to tell which members are used without pulling apart the functions that the ops are passed to. This usually develops as the complexity of a type or set of types increases, and they require additional parameters. Over time, the parameter list gets large, eventually too large, and then, like in this slide, the parameters are condensed down into a single options parameter. So, what members of options are being used here? Well, let's look. Here we see that ID, type, and other ID are the three fields that are actually required for the work that's being done. We had to dig down at least 2 levels to figure that out, and this is a simple example. Picture the option struct being imported and shared with other packages, especially as doer grows more methods that require different options. Imagine this pattern repeated over and over again in significantly more complex code. What is the impact to readability? What is the impact to simplicity? Here's a better way to write this code. It's somewhat obvious, right? doThing now takes a discrete set of inputs. It takes ID, type, other ID, uses those to calculate the URL of something using those inputs. In URL for things, these are mapped to variables whose names make more sense in the context of generating the URL. When reading the signature of doThing, you know what it needs. And because you're not copying the whole option struct, the amount of data being copied is reduced on each function call. So to review, config structs couple the package containing it to every other package that needs the config type. Coupling makes it easier to create non-orthogonal code. They obfuscate the API of the functions or types that accept the config struct. Unused config members create clutter. It papers over the fact that the functions or types are complex, possibly too complex, hiding the need for a redesign. So what are the options? The function or type only needs a few values. Well, just pass those values. If you have too many values, you can try a functional configuration approach. This style is my personal favorite. It's especially useful when the default or 0 values need to be tweaked. It also provides a mechanism for users to write their own functional options. Dave Cheney gave a functional options for friendly APIs talk and wrote a follow-up blog post that are a great guide. If that's still not enough, though, your functions and types are doing too much, you should consider redesigning them to be more focused. Pointer all the things. No, please just stop. I want you to consider what a pointer means. A pointer doesn't automatically mean it'll be faster. If you believe it'll be faster, well, benchmark it to prove it before committing to it. A pointer doesn't mean that less garbage will be created, although it can mean that less data is copied when a function is called. Taking a pointer allocates a second value, the pointer value, in addition to the value being pointed to. If the pointer value escapes the function that created it, it may be moved to the heap along with the value it points to. Pointers are about ownership. When you pass a pointer to a function, you're delegating ownership of the pointee to that function. So I'm not saying don't use pointers. I'm saying that you should be aware of the fact that you are sharing and decide when it's the correct action or not. In summary, pointers are about ownership. They aren't necessarily faster. And remember one of the Go proverbs: don't communicate by sharing memory, share memory by communicating. So I said we're going to talk about context. And let me start by saying that context.value, it's a trap. There are other ways to pass values along the request chain. I won't cover those here, frankly, though, because that's like a whole different talk. This example code was pulled from the blog post for context from golang.org. I see a problem with this code. We've now created a side channel, undocumented API for Google.search. Even worse, this undocumented API avoids the type system by wrapping everything in the empty interface. We'll discuss empty interfaces later. This makes the code less clear, less understandable, and the API less discoverable. Here's another take on that code. It's more in line with the explanation given in the context blog post, which states, the client's IP address is needed for backend requests. We see that Google Search now requires a net.ip, just like the blog post says it needs to. This is an expanded version of what was on the last slide. Note that a context.context is still a part of the search function. That's because the other properties of context are a very useful abstraction around signaling cancellation, as seen here in that HTTP do function. In summary, use value and with value sparingly. They create undocumented side channel APIs. If you still feel the need to use them, document the values that may be extracted from the context and the purpose of those values. Use with timeout, with cancel, with deadline, as they are a great abstraction around cancellation. Speaking of cancellation, the asynchronous API's pattern, anti-pattern. This code here is a simplified version of an API I wrote when I was starting out in Go. There are a bunch of problems with it, though. How's that Go routine going to be shut down? How is the size of that channel controlled? Closing the channel received from logs is likely to result in a panic. How do errors from the Go routine get communicated? And what if I need a synchronous API? Most of these issues can be handled by making the logs function take additional parameters, or even by making a new type and adding some methods to that type. But here's a synchronous version that answers all of those questions. We still have a type, but it has a much more accurate name, reader. The user of a reader value is in control of the reading loop and error handling. Next is called until it returns false, indicating no more logs, and provides the current item unless there is an error. Reader itself likely uses channels in an async fashion underneath in that read next function, especially since it can be canceled via the context. But those channels are not exposed. This synchronous API can make asynchronous if and when it's needed by its consumers. In summary, provide synchronous APIs. It is possible to make synchronous APIs async, but it's much harder, if not impossible, to do the inverse. Leave the concurrency to someone else. As a general rule, it should be uncommon to expose channels in an API. Use them internally instead. For inspiration, I urge you to see the HTTP package in the standard lib. That is a large package with a huge API surface and does quite a lot. It uses channels internally, but only exposes one in the closed notifier type. The if-then-else anti-pattern. This here is fairly idiomatic Ruby. It relies on the fact that functions in Ruby return the last evaluated statement. Foo is returned when x is greater than 2, because it was the last evaluated statement in the function. Otherwise, bar is returned, again, for the same reason. Directly transliterating this to Go, we would have a function that looks like this. And running it through the Go linter will produce the following warning. If block ends with return statement, so drop this else and outdent its block. The Go tools are there to help you. With that change implemented, we get this. The path with a conditional, x is greater than 2, is handled above the non-conditional path and returns early. The non-conditional path, also known as the happy path, is dedented to the left and is a simple return. Here's another example. It is harder to visually trace what is going on in the function to the left. But the function on the right handles the error conditions immediately. It returns an error and keeps the flow of the function aligned to the left, making visual parsing easier. Sometimes, though, it's not as easy. The code here is parsing some raw start and end times for an event. For brevity, the end time logic, which is almost identical to the start time logic, is elided. If the raw string time is empty, a default value is calculated and assigned to the event. If the raw time is not empty, the time is parsed. If there's an error in parsing, that error is returned and the function ends. If not, the parse time is assigned to the event. But it's visually harder to parse the flow of the function than it needs to be, and as I mentioned earlier, the end time logic still isn't shown here. Let's do better. In this new version, the function parseTimerDefault contains app-specific logic for parsing and returning a time. The parseTimerDefault and newThing functions handle error logic before the happy paths. There is a clean flow with the happy paths flushed to the left in both functions. And here, there's also enough space to include the end time handling. So to summarize, handle errors early and return often. Keep the common or happy paths dedented and to the left. When that's not possible, refactor or redesign. Panic in a lib. I hope you don't personally experience this, but I have. Panic is as close to exceptions as Go gets. In language that utilizes exceptions for error handling, raising an error is a natural thing. But in Go, errors are values that need to be handled. If the doHTTP function above was part of a third-party dependency, any app that uses it would need to add recover checks to every function that calls doHTTP, or risk having a panic bubble up and terminate the program. This forces the user of the dependency to litter defer functions around their code base. To further complicate matters, it may be a transitive dependency. So the panic may bubble up into the application even though it's not being used directly. You usually find out where to put recovery checks where they need to be added after the fact, after your program is crashing due to an unhandled panic at runtime, when it's in production. In Go, treating the error as a value and handling it is idiomatic. The error goes from being a nebulous part of the contract around using doHTTP to a part of the function's signature, making it discoverable via documentation and other tooling. So to summarize, return errors, don't panic. Only panic when an error can't be handled directly or the handling can't be delegated to the upstream caller. This should only happen when the program cannot make any forward progress. We didn't cover it, but I also encourage everyone to add context to their errors with the package.errors package before returning them. Interface all the things. So while I immediately grasped Go interfaces, it really took me a while to appreciate the power of small, simple, focused interfaces. This appreciation came when I realized it would be possible to re-implement a batch of logs sent to a HTTP service as an I/O reader. This change made the batch easier to send because Go's HTTP client works with I/O readers. This also improved performance by eliminating a copy into a buffer before making the HTTP call. Additionally, this same batch could be passed to anything taking an I/O reader, or even an I/O writer when adapted by an I/O pipe. That is when I internalized the potential of small, focused interfaces. But these days, I run into a lot of large interfaces. 6, 12, or even more methods. These large interfaces tend to also have only 2 implementations, the first being the only concrete implementation that I can find, the second being a mock for the purposes of testing. These large interfaces tend to be defined up front. They aren't discovered from implementations across the code base at a later date. They tend to not be an abstraction, but the encoding of already declared interactions. There is little to no abstractions in these interfaces, and they remind me of the Go proverb, the bigger the interface, the weaker the abstraction. Interfaces should be discovered from existing types and extracted out of them. The I/O reader and I/O writer interfaces were not designed up front. They were discovered later. The network, file, and other byte handling types shared a similar implementation. Out of those similarities, the I/O reader and I/O writer interfaces were born. The interface example in this slide isn't real, but it is extracted out of real code. The real one has more methods, 17 to be exact. The single concrete implementation of this interface talks to a service via HTTP. The only other implementation is the mock implementation. A different approach to the same problem domain would be to use the HTTP client and the standard lib instead. After all, the concrete implementation is a wrapper around HTTP requests. Create types for each of the domain concerns. Thing, thing hook, thing config, just replace thing with what's important. Each of those types has methods for each of the different interactions, each of which creates and returns a HTTP request for that interaction. This allows users of the API to use the standard HTTP client's do method. A nice side effect of this is that the HTTP test server can be used to test more of your code instead of testing a mock. This solution eliminates the giant interface, it uses more of the power of the standard lib, and improves test coverage. Duplicate. In summary, the bigger the interface, the weaker the abstraction. Rethinking the abstraction and perhaps pivoting away from what is being done to how it's being done can help, and sometimes, honestly, vice versa is also true. There are other ways to test things than mocking an interface. The HTTP test server, types handlers, and network servers are really pretty easy to write and go. I'm not against mocks, by the way. They just tend to be overused, especially when coupled with a large interface like this. And I've actually seen code where, really unbeknownst to some developer later on, ultimately what happens is the only thing they're doing is testing the mocks when they think they're testing something else. And that's just not good. The naked return values anti-pattern. Naked returns are often used with named return values. The above returns the random integer and the error. This is because n and error are named in the return parameters. But as this function grows, it's easy for naked returns to lead to subtle bugs. Here, small thing has been expanded to call something and handle the error. But if you expect to get the error from something returned to main, you'd be mistaken. This is because error is shadowed in the block. Once naked returns show up in code, they tend to stick around. They get cargo culted forward to new functions. They're not factored out as those functions expand. They inevitably cause subtle bugs. The guidance of the Go review comments section of the Golang wiki states, naked returns are okay if the function is a handful of lines. Once it's a medium-sized function, be explicit with your return values. Corollary, it's not worth it to name result parameters just because it enables you to use naked returns. Clarity of docs is always more important than saving a line or two in your function. I go one step further and say, you should not use naked return values at all, even when you use named result parameters. Empty interface. So what does this function voila know about the value I? To quote the Go proverbs, empty interface says nothing. The Go runtime, though, still knows what type the interface is wrapping. Above image shows the 2 pointers the runtime holds in an empty interface. The first is a pointer to the type the interface is wrapping, so the runtime knows what it is. The second is a pointer to the data itself. But voila here, we'll need to resort to type assertions or switch statements to determine how I should be handled. The empty interface sidesteps static type checking, and voila can't force any guarantees on the caller. What happens above is something other than an int, float 64, or string is passed to voila. Nothing? We didn't write a case for it. We can handle that case, but that's ultimately only useful eventually with a generic fall-through. Instead of using the empty interface, try to create an interface with a method that defines the behavior you need. And frankly, one may already exist. But sometimes we do need to use the empty interface, especially when dealing with unknown data or data that we will not inspect. This is commonly needed with encoding stuff, but this still requires a lot of reflection. If you're interested in exactly how much reflection, I urge you to read through the JSON package. In summary, use the empty interface when dealing with unknown data. Otherwise, try to tease out an interface that declares the behavior you need. Those are all the anti-patterns that I pretty much have time for and was able to generate slides for. So let's recap quickly, though. With regard to orthogonality, Idiomatic Go is made up of small pieces that do one thing well. This principle can be observed in small, focused interfaces that generalize behavior, not an implementation. In Go, packages, skip it. I don't even know what that sentence said, or what it was trying to say anymore. With regard to readability, Idiomatic Go has clear lines of sight. Functions declare the dependencies via their parameter lists, making it easy to understand what type of value is and where that type came from. A function's happy path is unindented, sitting all the way to the left. And the strategy of return early and return often is used before the happy path to handle errors. Idiomatic Go avoids stuttering, reducing cluster and noise. Idiomatic Go is well documented, focusing on the why of its packages, types, and functions. With regard to simplicity, Idiomatic Go uses empty interface sparingly and with care, both in test and non-test code. Packages and projects export a minimal surface area and have names that clearly indicate their purpose. I hope that through these anti-patterns, I've shown you some things to look for when writing and reviewing Go code. I hope I have shown how the design principles of the Go language help identify non-idiomatic code. And I'm sure these anti-patterns aren't complete, and I do look forward to future discussions. Thank you. Before questions, though, I'd like to extend a special thanks to Renee French for the Go Gopher, Alexander Shalakin, I've probably totally destroyed his name, for even more gophers, Sea of Clouds for the Go Haiku, my family for putting up with me while I focus on this talk instead of going to the pool, to scavenger hunts, and other things, to Dave Cheney, Inez Sombra, and Sam Boyer for helping whip this talk into shape, the entire Go team for creating a language that values the same things I value, the GopherCon team for putting this conference on every year, and last but certainly not least, everyone who attended today.